All right, let's begin with an example here. So, unbounded example. Let me make it a maximization problem this time. Of course, you can always change a maximization problem into a minimization problem by multiplying the cost vector by -1. Okay. For the case of maximization problem, of course, the only thing that changes is you look for an RK which is less than 0 rather than greater than 0. Okay. Maybe you should make a note of that. So in this case, we're going to look for a reduced cost which is negative, and the column underneath that variable should still be less than or equal to 0. Okay, there's no change there. So in this case, the initial solution is the following. Again, I'm choosing x3 and x4 as my initial basic variables. The identity matrix is my initial basis. So we have simply the original problem coefficients in the tableau. And the row 0 equation is, well, it's simply the negative of what you have in the objective function. That's it. In this case, I'm looking for an entering variable which is negative. And if I'm tempted to choose the most negative one, that's what I would choose. Except that I'm not going to choose that, because if I choose that, there's nothing wrong with that. Then these are positive entries, so of course, I can go through one iteration, get the new solution in terms of the new basic set of variables, and then still look for a unboundedness. Well, I know that there's unbounded. This problem is unbounded because by construction, that's what I did. So rather than choosing that one, let's choose that one. Okay? That has a negative number here, reduced cost. So the rate of change in z as a function of x2 is 1, which means it's going up by 1 unit for each unit increase in x2. There's no ratio to test for. All these numbers are negative or 0. So this column tells you that you have an unbounded problem. Okay? Unbounded means you can make your objective function as large as you wish for a maximization and still get a feasible solution. So let's find a feasible solution with objective value of 1 million, for example. Yes? How can we understand that this is unbounded? The following way. You look for, this is a maximization problem, so for improvement you need to identify a negative reduced cost. If there's a negative reduced cost for a maximization problem for which the column in the constraints portion of the tableau is either less than 0 or 0, in that case the problem is unbounded. Okay? Okay. That's how you detect unboundedness. If we actually entered x1 and went through one more iteration, we would have detected unboundedness in the new tableau, which is fine, no problem. But, you know, I'm lazy, so let's just do it here, okay? All right, so in this case, suppose I want to get an objective value of, say, 1 million, whatever. Could be larger than that if you wish. To do that, I'm going to enter x2. And the objective function tells me that z is, well, x1 is still kept 0, okay? Z is, well, or z minus x2 is equal to 0 when x1 is 0. x1 is still non-basic, okay? So this tells me that if I want a z value of 1 million, then x2 should be 1 million. I increase it to 1 million. Of course, if you had a different coefficient here, you know, you could have computed that, okay, by how much you should increase. You just substitute 1 million for z and then solve for x2. That's it. And then x3 and x4 are dependent on x2. x3 is equal to 10 plus x2 from here. And the other one is equal to 40 plus 0 times, sorry, not x2. Yes, it is x2. The other one will be 40 plus 0 times x2, so it won't change. But this one changes, of course. How much will it be? 1 million and 10. That's how much it will be. So the solution we're talking about is the x solution that has a 0 for x1 because it's non-basic. x2 is 1 million. I should have picked a smaller number, too many zeros here. x3 is 1 million and 10. x4 is 40. And z is clearly 1 million. Is this feasible? Do you think this is a feasible solution? It is. By construction it is. Because these equations tell you that you're always satisfying the original set of equations. And non-negativity is also satisfied, so it is feasible. Okay? Is the objective value truly 1 million? Let's check. 2 times x1. Well, x1 is 0, so, you know, it doesn't change. But x2 is 1 million, so yes, z equals 1 million. And if you plug in the values of these constants for the variables, you will see that you are satisfying the equations. So it is truly feasible. Is it basic feasible? Louder. Yes or no? She says no. How many people say no? You say no. How many people say yes? How many people say I am neutral? I have no idea. Huh? Okay. Well, you're right. It's not basic. This is only feasible. But it's not basic because obviously it's got 3 positive components. It is not basic, okay? You perturb the basic solution, x3, x4, plus the other ones are 0. You moved in a direction, you added x2, so you obtain the feasible solution, which gives you the desired value, okay? It's not basic though. course, to be able to initiate the simplex method, you need to begin with a basis or an initial basic feasible solution. Once you initiate, you know how to get going, okay, from one tableau to the next one. This is an important topic, and it's a new chapter actually in your book, so we're switching a chapter now, okay? Chapter 3 is finished just about. There are easy ways of finding an initial basic feasible solutions, and there are also the difficult cases. But let's just look at the easy case first. So this is the easy case. Suppose you're minimizing Cx subject to Ax less than or equal to b, x greater than or equal to 0. Assume b is non-negative. So I put all my vectors, all my constraints in less than or equal to 1. Suppose that's the case, okay? And standard form of the problem will then give you the minimization of Cx subject to Ax plus a vector of slack variables equals b, with x and slacks being non-negative. Okay? S stands for a vector of slack variables. I'm assuming rank of A is, again, m, the number of rows of A. Okay? In this case, it's really easy to start with S being the basic, initial basic set of variables. So in this case, initial basic variables are the slacks. The slacks are equal to b because the x portion, they are non-basic, they are 0, and I assumed b is non-negative, so non-negativity is not jeopardized here. Okay, it's satisfied. And the objective value is, of course, 0. That's the initial basic feasible solution. The identity is your initial basis because you have an identity in front of your S here. Okay? So that's the easy case. And the initial example I gave you at the very beginning was of this case, so we did not trouble with the finding of an initial basic feasible solution. Still an easy case, but without the slacks. A little bit more difficult, maybe. Okay? You're still minimizing some objective function Cx subject to some constraints, except that I partitioned my variables into two parts, x and, say, x cap. So the x caps, or let's make it x tilde rather, the x tilde part has an identity as its columns. It has whatever cost it has, say, call it c tilde. Okay? So the variables are in such a way that some of the variables form the identity matrix of the appropriate size. Everything is non-negative again. This is the standard form problem. In this case, of course, the problem in row 0 form looks like the following. You again introduce your additional variable z, and you minimize. Of course, these things could be also discussed for maximization problem, but nevertheless, let's just stick to minimization. Row 0 form will be minimization of z subject to z minus cx minus c tilde x tilde equals 0 with ax plus identity x tilde equals b here. I'm assuming b is again non-negative. So let's make that assumption. Assume B is non-negative again. Otherwise, it won't work. Okay? In this case, begin again with x tilde as your basic set of variables. Okay? So this corresponds to having a B matrix of identity because x tilde has identity. Okay? What is the initial solution? Well, the initial basic feasible solution is obtained by setting x equals 0. That's the non-basic part. Then the basic part, x tilde, is solved using, by the way, you've got non-negativity here, which I forgot, is solved by using the lower part of the boxed equations. So x is equal to 0, x tilde is b. It's just simply the current right-hand side, which is by assumption non-negative, so it's basic feasible. And the objective value z is how much? C tilde times b. That's what you should have for z. Okay? What is the initial tableau for this one? Well, the lower part will be B inverse, which is identity times A, and identity times identity. So you've got this in the lower part. Okay? Everything is pre-multiplied by B inverse. In this case, it's identity. At the top, well, you can write it this way, minus C here and minus C tilde here with a 0 here. But that would be incorrect. Why? Because you want to actually have 0 here. Okay? How do you get your 0? Well, if you add the row vector C tilde times identity added to the top row, you will get that. In which case, of course, this will become how much? Well, let me do it here. So this is the wrong tableau, okay? This is not correct because the top part is incorrect. The correct version is obtained after pre-multiplying the lower part by C tilde and adding it to row 0. In which case we have 1, 0, A, identity, B, C tilde times A minus C. That's what you've got here. For this part, C tilde times identity minus C tilde, which gives you 0. Here you've got C tilde times B. Of course, C tilde B is your current objective value, so it agrees. At least we have that. And etc. The other parts. So, reduced costs. The vector of reduced costs has C tilde A minus C for the x part, 0 for the x tilde part. Okay? It's easy. The only thing is you need to modify row 0 before you begin doing any operations. That's all. I'm not going to give you an example for this. You should be able to work it out on your own. Okay? Now the more difficult case. Is it party time? Music. Okay, the distinguishing feature of the easy cases, either the first or the second one, is that initially you have an identity matrix from the standard form problem. But sometimes you will not have that situation. There is no identity in the standard form version of the problem. Let's say more difficult. It's not really difficult, the more difficult case. Okay? The standard form of the problem does not have enough unit vectors in it, does not have the identity matrix I in it. What size I do you want? I stands for the identity here, m by m. Okay? You want m by m. Assuming, of course, the rank of the equation portion of the constraints is the row rank. Okay? Now, the initial matrix of coefficients may have certain columns or some of the columns of the identity. Nevertheless, even if it has a single column that's missing, you still have a difficult case. Okay? So in that case, we insert. So let's do it this way. The initial problem is the minimization of, say, Cx subject to Ax equals b, x greater than or equal to 0. That's your standard form problem. And A does not have an m by m identity in it. Okay? So you cannot form the initial basis. Now, before I go ahead and do anything here, you may be tempted to choose an initial set of m columns that are linearly independent and begin with that. All you have to do is, once you have your B matrix formed by linearly independent m columns out of the columns of A, that's certainly a valid basis. So you can compute B inverse and form the problem, in the altered form, etc. What is the difficulty with that? If you know that the basis you picked happens to be a feasible basis, fine. Go ahead and do it if you wish. Nobody can stop you. Okay? But if you don't know if it's a feasible basis, then you have a problem. What does it mean for initial basis to be not feasible? Well, you set the non-basic variables equal to 0, solve for xb. So you get for xb, you get b inverse times b. But that b inverse b is supposed to be greater than or equal to 0. But if it's not, no, it's not less than. It's not. So b inverse times b, which is the value you get for xb, you want it to be this way. If this is ensured, fine, you can begin with that. But if it's not ensured, if it turns out that it has a negative component, at least one negative component, in that case, of course, you have to try some other basis. So there's no end to trying. Some people are patient. They keep trying all the time until they discover a feasible basis. It may take too much time for you. And you may actually end up having no feasible basis, actually, because the problem may be infeasible, actually. You never know. Okay? So you need a more intelligent way of approaching this problem. Okay? Instead of just trial and error, you want to begin with something more intelligent. In that case, what we do is we perturb the problem to make it look like the following. So if this is my initial problem, I perturb it, make it p prime. I add identity times x sub a vector of variables x sub a, So I simply added new variables and new columns. The new columns have the or form the identity. And of course, let's forget the objective function for a moment. Well, actually, let's not forget. We'll add something to the objective function for the new variables, okay? And here, xa is the m vector of artificial variables. Now, forget the objective function for a moment. I changed the problem. So what you need to observe is the following. Observe the following. X is feasible to AX equals B, or let's make it a particular one. X bar is feasible to AX equals B, in other words, satisfies this. And of course, I'm assuming non-negativity is satisfied. Okay? If and only if AX bar plus XA equals B, let me put it this way. If and only if X bar and XA is feasible to AX plus XA equals B with XA equals 0. Okay, let's just write it that way. So, whenever X bar is feasible to AX bar, AX equals B, it should be the case that the enlarged vector, or the extended vector with XA included, is feasible to the extended system or the new system with XA equal 0. So that AX equals B is satisfied. Okay? All right. So what do we do here? Hence, we begin with XA as initial basic feasible solution or basic set of variables, but want to obtain XA equals 0 when we optimize. Or for a maximization problem, as you maximize the objective function, you still want XA equals 0, okay? Hence, we penalize these artificial variables. So the variables inside XA are called artificial variables, and they have no business being in the problem. The problem is changed. Whenever they are non-zero, the original a feasible solution to the problem with XA non-zero, at least some component is non-zero, is not feasible to the original problem. So you want to make sure that using the sense of optimization in the objective function, they are being penalized. Since this is a minimization problem, the penalty is, of course, the following. You add a positive number m times, very large number m, times the artificial variables, say, let's call them x sub j, x sub a sub j, where m is a very large positive number, very large. as large as your computer can take, for example. Rather than writing a specific number for that, all this is trying to do is, it's whenever some artificial variable is positive in a feasible solution to the perturbed problem or to the new problem, then the positive coefficient, even if xaj is very small, will make this very large, so the minimum value will be far away from the true minimum. Okay? So in an attempt to minimize this objective function, of course, you are hoping that all of the xaj's will become eventually 0 through the iterations, and then finally you will get a true optimum value. This is called the big M method. There's really nothing mysterious to it. You're just adding artificial variables, which are variables that don't belong to the original problem, and you penalize them in the objective function to make sure that through an attempt to minimize or optimize, they eventually become all 0. Let me give you an example of this. That's the standard form of the initial problem. So this is your P here in standard form. X4 is a slack variable. X3 is a surplus variable, okay, excess variable. Now I need a 3 by 3 identity matrix here, but I don't have it. I have only one column of the identity, the third column, 0, 0, 1. The other two columns are missing. So in this case, all you have to do is to supply the missing columns of the identity, which means you add 2 artificial variables. You can also add 3 artificial variables. Of course, in this description, I made it look like you're adding as many artificial variables as there are constraints, but you can actually add fewer than that. Otherwise, notationally, it becomes difficult. So here, I'm going to define a new problem, which is essentially the same old problem, except that we have new variables. So the new variables, let me make them in different color. I add x5, which has the unit vector 1, 0, 0. And I add x sub 6, which has the unit vector 0, 1, 0. So all the columns of the identity will be supplied now. And of course, for that reason, we penalize x5 and x6 in the objective function. That's your new problem. And we hope to get an optimal basic feasible solution to this problem, which is also optimal to the original problem. Okay? So, we solve P prime. which is also optimal to the original problem if all artificial variables are 0. If it is the case that at least one artificial variable is positive, that means the new problem is, yes, it has an optimal solution, but the original problem is infeasible. It does not admit a feasible solution. Okay, make a note of that. So, we begin with the following tableau. I'm going to use x4 as part of the basic variables because it has the column 0, 0, 1. So we have 3. Okay, so this is 0 all the way. 3, 4, 1. 1, 3, 2. And if you write the objective function with all variables on the left side, that's what you get for row 0. This is your system of equations to begin with. The initial basic feasible solution has both artificial variables at positive level, so this is feasible to the original, feasible to the new problem, but not feasible to the original problem. Okay. The top row is not in the appropriate form. I need 0 for x5 and 0 for x6 because the reduced costs are 0. You can compute your reduced cost using the definition Rj equals CB B inverse Aj minus Cj. This always gives you, that's the safe way of doing it. Of course, B here is identity, so CB, what is CB in this case? So CB is what vector? It's the costs, vector of costs associated with the basic variables. x5 has a basic cost of m, x6 has m, x4 has 0, times the appropriate column minus Cj. That's the way you compute. But easier way is to simply zero them out using appropriate multiples of the other rows here. So if you multiply this row by m and row 1 and row 2 by m and add it to the top row, you achieve the same thing. They are equivalent operations. So that will give me a revised version of this, which will give you 3 plus 4, 7m minus 4. The minus 4 stays there. Okay. This one gives you 4m minus 1. This gives you minus m. This is still 0. This one is what? 0. This one is 0. This one is 3 plus 6, 9m. So the new numbers are 7m minus 4. Let me make them red. They are the revised numbers. Okay, that's the way they are. Okay. Now we're trying to minimize here. By the way, if this were a maximization problem, what would be the situation then for the penalties? Minus m, of course. You would be penalizing in the reverse direction. Okay, so maybe you should make a note of that as well. Of course, I'm assuming also that you're reading your book. These are discussed in detail in the book as well. I'm giving you the highlights. So once you get the highlights, of course, you should make the appropriate transformations in your head. for minimization to maximization, etc. All right, here we look for a most positive reduced cost. In this case, of course, m dominates all the constants, so 7m is larger than 4m, so you choose that one. You can also choose the 4m as well. And then you look at your ratios, 3 to 3, 6 to 4, 4 to 1. 3 to 3 is your minimum. You pivot on that. And when you do that, you get the following. X2 has a reduced cost of 5/3 m plus 1/3. X3 has a reduced cost of minus m. X4 has 0. X5 has minus 7/3 m plus 4/3. X6 has, well, it's basic, so it's 0. And the right side is 2m plus 4. We're just doing the regular pivoting operations, except that this m is, of course, a little bit difficult to manipulate. Nevertheless, you can do it. Okay. All right, so we have 1/3 here, 5/3, 5/3, 0, minus 1, and 0. 0, 0, 1, 1/3, minus 4/3, minus 1/3, 0, 0, 1, 0 for the last column, and 1, 2, 3 for the right side. That's your new basic feasible solution. Well, x5, which is your artificial variable in the initial solution, is 0 now. Also, you want to get rid of x6. x6 is still positive, okay? So this is still not feasible to the original problem. So we enter another one, if we find one. It is this one. And then we look at the ratios. It's hard to see which one is minimum, but I guess the minimum is 5/3. That's that one. Yeah, you pivot on this one. When you pivot, you get the new solution. Okay, so you've got this solution. Now, both artificial variables are non-basic, they are 0, so a basic feasible solution to P is available now, is at hand. What is it? x1 is 3/5, x2 is 6/5, x4 is 1, x3 is 0, x5, x6, they have no business, they are 0. So you drop those two columns. I'll just drop it here, erase them. And you work with the persisting columns. And then when you do that, is there an entering variable? Yes, this is a minimization, so you can still enter that. And then, of course, something else exits here. It's this one. And then, finally, we have a better basic feasible solution, z, x1, x2, x3, x4. See, when most of the variables are basic, it's easier to fill in the tableau. It's just unit vectors. X4 column is -1/5, -1/5, 3/5, and 1. The right sides are 2/5, 9/5, 1, and 17/5. Yes, this one is better than the previous one. 18/5 went down to 17/5, which is a little bit smaller. And this is optimal because there's no reduced cost, which is positive here. Optimum to P prime, which is also optimal to P. The original problem, okay? Let's stop here. We're out of time. There's an alternative method which I'm going to discuss in the next hour on Wednesday.